Hello everyone, I'm Shivani and welcome to Civil series. So this is the part 4, last part of theory of structure short notes. So in this video we are going to cover the moment distribution, then slope deflection and remaining many of the points which are stiffness, relative stiffness, distribution factor and carryover factor. These are the points for this video. Okay, so let's start the video. Here the point is moment distribution method. Okay, let's take one example here. So here this is a structure. Okay, you can say it as a frame structure. This is support A, B and O. If we apply a moment at joint O, this is M. If we apply a moment at joint O, then moment distribution, distribution on member OA and OB. Okay, OA is one member and OB is the second member. Moment distribution on both members in that EI. Okay, this is flexural rigidity of OA is greater than flexural rigidity of OB. Okay, that is if this happens. Okay, that is if this happens, that is the member OA is more stronger and stiff, okay, and then according to MDM movement distribution method, if member is stiffer, then that attracts more movement. Okay, okay, then the movement in case of OA member is more than the movement in the member OB. Okay, this is the physical meaning of the MDM movement distribution method. Okay, this is how it goes. If the EI means flexural rigidity of any member is larger than the EI. Okay, so this is an example. If we take the value of the I is here 2I and take I as here I value is I, then this is an example. Okay, here 2I is more than the I. Okay, so this happens here. This EI is automatically increased than the EI of OB. Okay, so the movement in case of the member OA is larger than the OB, as that member OA is more stiffer and more stronger. Okay, stiffness is represented by K. Okay, stiffness is represented by K, and stiffness is the value or the moment produced by unit deflection or unit rotation. Stiffness is the value of load or moment. Stiffness is the value of load or moment that produce unit deflection. Okay, that produce unit deflection or unit rotation. Okay, there are two type of stiffness. First stiffness is axial stiffness, and second stiffness is bending stiffness. Okay, so here the load and moment value distribute here. Okay, so the value of load which produce unit deflection in case of axial stiffness, and value of movement produce unit rotation here in case of bending stiffness. Okay, so the formula for stiffness is K is equals to axial stiffness is equals to AE by L. Okay, this is the axial stiffness, and AE is nothing but axial rigidity. Okay, then for bending stiffness there are three conditions. In that, first one is if far end is fixed. If far end is fixed, then K value is equals to 4 EI by L. If far end is hinge or roller, then K value is equal to 3 EI by L. Third, if far end is free, then K is equal to 0. These are the three values of stiffness for different end conditions. Okay, so this is how the two types of stiffness, bending and axial stiffness. Okay, these are the formulas. Okay, so write these formulas. These are the important formulas. Here the EI is equal to flexural stiffness, or you can say it as a bending stiffness. Then next we'll see the stiffness at joint. Okay, so here we see about the stiffness at joint. Okay, stiffness at joint. Stiffness at joint is represented by summation of K or K naught. Okay, and K naught, if consider this is a frame structure. Okay, this is one of the frame structure. This is hinge support. Okay, so here the support is A, this is B, and C and O. Okay, L is a length, EI is the flexural stiffness, L is a length, EI is a flexural stiffness, L is length and EI is a flexural stiffness for all the three members. Then K naught is equal to summation of stiffness at member, meeting at joint. Okay, so first member OA, so take it as KOA, stiffness of OA member, stiffness of OC member, stiffness of OB member. Okay, so take this joint or O joint as a center, and from this O the A support is fixed, means far end is fixed here, so the K value or stiffness value is 4 EI by L plus KOC. Okay, in case of OC member, the far end is free, then the stiffness value is equal to 0, plus in case of OB, the far end is hinge, then the stiffness value is 3 EI by L. By adding this, we get 7 EI by L, and this 7 EI by L is nothing but a stiffness at joint. Okay, the individual value about the end condition is stiffness of member, and addition of all the stiffness at members is nothing but stiffness at joint. Then distribution factor. Distribution factor is represent like this, DF. DF is a ratio of stiffness. DF is a ratio of stiffness at member to stiffness at joint. This is the formula to calculate the distribution factor. Okay, DF is equal to K divided by summation of K or K naught. Okay, the moment in case of stiffness is always distribute in opposite sign. This is the important point from this formula is stiffness at member to stiffness at joint. This is how you can calculate the distribution factor. Carryover factor is a ratio of movement transfer at far end to movement transfer at near end. Okay, this is the carryover factor, ratio of movement transfer at far end to movement transfer at near end. In that, four conditions are there. First condition, if far end is fixed. Okay, so the movement transfer at the far end is half. Okay, so if this is the beam and here for example here the moment act is m. Okay, for example here the moment act is equal to m, then moment transfer on this end is m by 2. Okay, so this is how the carryover factor works. Then next, if far end is hinge or roller, then moment transfer or the carryover factor transferred is 0. Then third is far end is free. Far end is free. Here also carryover factor is equal to 0. Then fourth condition is when internal hinge is present. When internal hinge is present, then carryover factor is equals to mb by a. mb by a. Okay, this is the value. If a is equal to b is equal to l by 2, then the carryover factor is equal to 1. Okay, so this is how you can calculate the carryover factor for different beam or frame conditions. And carryover factor transferred with the same sign. Carryover factor transferred with same sign, but moment transfer with opposite sign. Okay, this is the important point. Carryover factor transfer with same sign. The next point is relative stiffness. Relative stiffness is a ratio of stiffness. Relative stiffness is a ratio of stiffness divided by Young's modulus of elasticity. In that first condition, if far end is fixed, then the relative stiffness is equals to, for far end the stiffness is 4 EI by L divided by Young's modulus. Then value of relative stiffness for far end is fixed is 4I by L. Then second, far end is hinge or roller. Far end is hinge or roller. Then the relative stiffness is equals to, here the stiffness is 3 EI by L divided by Young's modulus 3I by L. This is the value of far end. This is the value of relative stiffness when far end is roller or hinge. Then third is far end is free. Far end is free. The value of stiffness here is equal to 0. So total relative stiffness value after calculation we get 0. Okay, so these are the relative stiffness values. And last condition is if internal hinge is present. If internal hinge is present, if this is the beam and in that beam internal hinge is present, A and this is B distance, then the relative stiffness is equal to, so this is the formula to calculate the relative stiffness, 3I A square divided by A cube plus B cube. And if the internal hinge is present at center, then A is equals to L by 2 and B is also equal to L by 2. Relative stiffness for that condition is 3I by L. If you put the values of A and B into this equation, you get the relative stiffness values. If internal hinge is present at center, then the relative stiffness is 3EI by L. The next point is fixed end moment. So the fixed end moment point is covered in the previous video, which is in short notes of strength of material. So in that video I cover a chart related to fixed end moment. In that I go for many of the conditions of beam with different loadings on that beam, and there we calculate a fixed end moments. But there are two fixed end moments or two settlements in case of fixed end moments. We are not discussed in that video, so we discuss here. So the fixed end moments due to settlement of supports are fixed end moments due to settlement of supports are first condition, if this is fixed beam. Okay, this fixed beam is settled down up to this point, up to delta. Okay, then the moment for this fixed beam about MAB this is support A, this is B, and about moment BA is equal. Okay, and that value is equals to 6 EI delta divided by L square. Okay, moment for both ends is same, that is 6 EI delta by L square. Then next, if far end is hinge and that hinge support is settled down, then the value of moment at AB is equals to this this is support A, this is B, and that value is equals to minus of 3 EI delta by L square, 3 EI delta by L square. But in case of moment of BA, that value is equals to 0. So these are the values for the settlement of supports. Then slope deflection method. So in the slope deflection method, there are two type of equations are formed. In that, first is joint equilibrium equation, and second equation is shear equation. Okay, these are the two type of equations here. So here the number of joint equilibrium equations are equals to number of unknown rotation, and in this the number of shear equation formed here, number of joint equilibrium equation formed is equals to number of unknown rotations, and here the number of shear equations formed are equals to number of unknown displacement. Okay, so here we consider one example to differentiate a difference between joint equilibrium equation and shear equation. So this is one example. This is a frame with fixed support. Okay, this is A, B, C and D. So here joint equilibrium equations are required in number 2, or two joint equilibrium equations are required to solve these kind of a frame, because two supports are there or two joints are there except the supports, and here one shear equation is required to solve this beam. So first we know about the joint equilibrium equation. So in that, at joint B, the joint equilibrium equation is MBC plus MBA is equal to 0, and at joint C, MCD plus MCB is equal to 0. So this is the joint equilibrium equation, and shear equation is MAB plus MBA divided by L plus MCD plus MDC divided by L is equal to 0. So these are the shear equation and joint equilibrium equations for solving these kind of frames. Then next is the slope deflection equation. So here this is an example of a frame with fixed support at both end and a 1 point load on the span, which is P, and the slope deflection equation for span AB and BA is, so here the MAB is equals to MAB bar plus 2EI divided by L into twice of theta A plus theta B. Then moment of BA is equals to MBA bar plus 2EI divided by L in bracket twice of theta B plus theta A. So this is how you can calculate the span, or this is how you can calculate the slope deflection equations for span AB and BA, and the same equations for span BC and CB, then for span CD and DC. So you can calculate the values of these span like this. Okay, just replace the value of A with B for this, and here B with C. Then to calculate CB, replace this B with C and this A with B. Okay, this is how you can calculate the slope deflection for the remaining span too. Okay, so here we end with a syllabus of theory of structure completely as a short notes. And okay, so here we completed two subjects, strength of material and TOS. And in the few days we start a new syllabus or new topic, new subject which is related to BMC. And stay tuned for that, and thank you for watching.